Okay, so for today, we are going to jump in. We're going a little bit further in depth. So just to take a little trip through like the last month, we started our jump after the break was chapter 14. We looked at solids, liquids, and gases. We saw how the atoms, or at least the particles, behave, how fast they wiggle, right? Okay, from there, we looked at some properties of fluid with pressure and all that good stuff. We looked at what matter is made of. Okay, jumping forward to the next chapter, we saw classifying matter. Liquid, solid, gas. We saw phase change and all that good stuff. 16, we made the transition. Instead of calling them particles, we started looking at the indivisibly small particles of matter that we're all inevitably made of. The atoms. What are atoms made of? Where do they show up on the periodic table and why? All that good stuff. We are making the transition at this point from the world of physics into the world of chemistry. So they're fairly related, which makes sense because everything's made of atoms. But today, we are going to start chapter 17, and we'll get this set up. And in chapter 17, as we're looking, trying to tell you how many sections there are. I think there's only three sections. But chapter 17, we are going to be going a bit more in depth, and we're going to be looking at the elements a little bit more. But instead of just saying what are they made of, we're going to be looking at elements and their properties. Okay, so you guys already did a little bit of this research just on your own, and I heard a lot of different properties as we look at them. In 17.1, we are going to look at one very particular type of element that shows up on the table, and we're just going to take a quick little recall trip without writing it. There are three, there's really four, but we're going to say there's three states of matter that things can exist in. Can you give me all three of them? Solid, liquid, gas. Does everything exist as all three? Not everything all the time. Some things go directly from solid to being a gas. Depends on pressures and stuff. Under normal conditions, they do not all satisfy all this stuff. Okay, now, on the periodic table, there's also three types of matter. Not solid, liquid, gas. That's not what I'm looking for. Without looking at the periodic table, I'm going to say one of them is nonmetals. Do you remember the other two? Metalloids.
Non-metalloids.
And metals, or just, yeah, I'm fine with that. And there's a fourth, I heard somebody over there, synthetic. They show up in such small amounts of time or in such specific settings, we're not going to focus on them yet. So, today we're going to do 17.1 and prepare to mosh because we are looking at metal. Or, no? All right, fair. I thought it was clever. Okay, so right off the bat, you guys have all touched a metal at some point, like you're sitting in a desk that has metal on it. What is metal? How would you describe it to somebody?
Hard. Silver.
So it's solid is what I'm going to use. You talk about the hardness of it. I like it. The metal on your desk is silver?
Yeah.
Down at the bottom, what about the other one?
This is metal?
Does it feel like metal?
Is metal and steel the same thing?
Ooh, is steel a metal?
Yes. Oh.
That seems reasonable. Okay, so if I generally ask, what color's metal? How do you answer it?
Gray.
Chrome.
No, gray?
Gray?
No.
Silver?
Chrome, silver?
Metallic.
So I like that language. Now it seems silly. Metallic, though, like it doesn't really sound silly or seem silly, but they're metal colored, right? Okay, most metals, when we look at them, they are that silver gray color, like depending on the situation. Even when it's a liquid, mercury just looks like liquid silver, or chrome, if you will. Okay, so as we're looking at this, we are going to sneak in right off the bat. We're talking about metals. We need a solid definition of what a metal actually is. Now, it turns out that there are a ton of characteristics that we don't have to go through super slow. We're going to try to make sense of it. Okay, elements that are, and this is a small list, and some of the words you'll recognize, but definitely not all of them. So here we go. Metals, by definition, for our purposes at least, are going to be elements that are, and we're going to have a small little list, and we're going to see how many of these words you know. Okay. If we talk about a metal, you guys said that they are silvery colored. If you have the pure form of it, meaning like it's not mixed with other stuff, like a gold nugget that you pick out of the river, probably not as shiny as gold that you'd find that's been refined, right? Because all the impurities have been taken out. Is gold shiny? Like you can make it shiny, but if it's pure and clean, it will be shiny. Others that are shiny? Any other metals? Silver is shiny. Mercury, I would say, is shiny. Most of them have some amount of shine to them, with very few exceptions. So, right off the bat, we're going to say they are, we're going to use a fancier word, lustrous. Okay, luster just means exactly what you guys are telling me there about the shininess. Shiny is another word that we can use. Lustrous is the real word. Anybody recognize that one? Lustrous? Okay. Maybe some of us, maybe not everybody. Okay. Furthermore, we're going to say that these guys are malleable. I'll make that a comma. Malleable. What does malleable mean? Say that again? Not shiny. So I don't think it could be shiny and not shiny. Just those two wouldn't work. When we talk about malleable, some metals are much more malleable than others. If you give me a piece of steel, can I bend it? What if you give me something, I'm trying to think, a smaller piece of like aluminum? Could I bend that one? Okay, so when we talk about malleable, we're just going to think bendy. And I'm going to say bendable with the understanding that it is not by human hand necessarily. It could be by bender if you watch Futurama. That works fine. Can it be bent? It probably a metal. When we compare it with something that's very clearly not a metal. So for example, you guys said you'd seen a brick of sulfur or a brick of charcoal, carbon. If I tried to take carbon and bend it, a brick of, like, stick of lead, does it bend? It breaks, right? It shatters. That's not malleable. Okay, couple more. We get a new word, ductile. I don't know why this one's coming out in all caps. It is no more vocab than the others. Bless you. Ductile. So it makes me think of ducks up in the ceiling is what it makes me think of. It is not sticky. That's a good thought, though. Any guess on ductile? Ooh, you can draw it out. So I'm cool with that. Can be drawn out into predominantly, copper is really ductile, and we use copper to make what? So it could be coins, but there's a lot more common stuff. Wires. So ductile, we'll say stretched or rolled. Because it's not really a true stretching that happens. We have to roll it into the wires, but it can be stretched out. Ductile. Okay. And last but not least, most metals, not every single one of them, but most metals do an okay job of letting electrons flow through them from one end to the next. Gosh, electrons. The flow of electrons, what do we call that again? So viscosity is how thick a liquid is. I like that your head's there. Say it again. So you're closer. Sonny said voltage. I'm asking, what is the flow of electrons? Voltage. It's not voltage. Voltage is what pushes electrons. What did you say? Okay. Related to voltage, what are the other two? Voltage is one of them. Resistance, and what was the third one? Current. Okay. Does electricity seem to pass through metal? Yeah, most of the time. Conductive. Okay. If you had all these properties, and I'm going to say electricity through. If you have all these properties, there's a pretty good chance that you have metal as we're looking at it. Okay. Now, as we go a little bit further, metals and the periodic table. So, like we've done before, we should have at least one on each desk is what I'd recommend. Have a periodic table open. So if you need a minute to grab a book, open up a periodic table, because we're going to be referencing it. So I'll let each group choose. Get a periodic table in front of you. The back cover of your text is the easiest option. The blue one. So I didn't ask which color. I said where on the table.
Almost everywhere.
So almost everywhere. But is there any particular region where it's not metal?
The right side.
So the right side. So everything left of seemingly the stairs. If I make that comment and I say metals are everything left of the stairs, do you know what I'm referring to? What are the stairs I'm talking about on your periodic table? The green part, the metalloids. So if we're looking at where these things are on the table, we'll say metals on periodic table. Okay. In your book, it is super nice because everything is color-coded right there. Do you think every periodic table has that? Definitely not. So Don't get just used to the colors. If you use your text, the colors will always be the same. But if you're in a different place, using a different book, whatever the case might be, then it won't work. We're going to say everything, and there's a little caveat in here, which just means something we have to pay attention to. Everything left, excuse me. Excuse me. Thank you. Everything left of metalloids, and I'm going to say metalloid stairs. And this is a Holloway thing. I think you'll probably, if you made that comment to any other place that you're learning chemistry, they would understand it. Okay. Specifically, everything left of the metalloids with one exception. There's one weird one that is to the left of all that, but not a metal. Hydrogen. Hydrogen is the odd man out there. Now, for these, remember the group numbers. First off, show me with a chop, not somebody else. Show me a group. You're going to chop this way or this way. Which one's groups? Okay, groups are vertical. What do the group numbers mean for groups 1, 2, or 13 through 18? Like, how do we use those? So I heard outer. Outer what? Electrons. In the highest energy level is what I think Lily's looking for. Okay, what's the other word? Outer and valence. Okay, now, notice, I've never once asked you to go to element number 32, vanadium. 23. I can't tell them upside down. 23, it's group 5. I've never asked you how many valence electrons are in vanadium, because that's in that weird part of the table, right? The transition metals in between. We cannot use that rule for the group number with anything other than 1, 2, and 13 through 18. Okay, I wish, 1, that there was a nice way to remember this, and 2, that we had the chemical knowledge to make sense of this, but we're going to make a generalized statement that's not always true, but most of the time is true. Metals. Metals normally, I'll underline that. That's what allows us to not be like true lie here. Metals normally have 1, 2, or 3 valence electrons. Okay. 1, 2, or 3. Now, when we look at this, we can start to think of how do metals connect with other stuff. So we have, obviously, iron is a metal. It's Fe. If we have iron oxide, which is just a fancy name for rust, we have a metal bonding with a non-metal. What did we say table salt was? Anybody remember the chemical formula for table salt? NaCl. Na for sodium, which is metal, metalloid, or non-metal? Sodium. Don't guess. It's a metal. Where is sodium?
Oh, wait, never mind. Oh, yes.
It's group 1. Now, normally, sodium in that form likes to bond with chlorine. Where is chlorine on your table?
Non-metal.
Non-metal. So check this out. We're going to hit this, and it's going to show up over and over. Can anybody remind me of the number of electrons that make something stable? 8. If I have 3 extra electrons, or 2 or 1, and I want to get to 8, there's 2 ways that we can do it. I can either add electrons to this, which if I had 3 valence electrons, I have to add 5 more. Do you agree with that? Okay. We're going to hit this real quick. I'm going to pause it and we're going to review something because it might not have clicked before. I don't need to pause it even. If I got rid of 3 electrons, how many valence electrons would I have?
From 8?
Well, just from something big, for example. So that's a weird idea, right? Okay. So check it out. In case this idea wasn't really clear, I'm going to pause it here. This is not today's stuff, but I want to make sure that we have this locked in. The fact that metals have 1, 2, or 3, is it easier to get rid of 1 or 2 or 3 electrons, or is it easier to bring in 5 or 6 or 7 of them? It is so much easier to get rid of them, right? Okay, we get rid of them, which means as we're looking at this and we're focusing on the idea of metals, with these 1, 2, or 3 valence electrons, we have a really common type of bond that happens. Metal, it bonds with something that wants to take those extra electrons. Metals like to get rid of them because they normally don't have up to 4. It's easier to get rid than gain. Is there anything on your table that's going to accept extra ones? Like it's almost full, but it's not quite full. So all the metals have 1, 2, or 3 valence electrons. Is there anything on your periodic table that has 5 or 6 or 7 valence electrons? Anywhere on the table? Fluoride, chlorine, sulfur, all these yellow things, right? Which means metal bonds really well with what other type of element? Non-metals. And I hate that this is so bold, but the fact that metals like to get rid of their electrons to be stable, and the whole right half of the table, at least 13 through 18, is really close to being like stable by just taking 1 or 2 or 3 electrons, it makes sense that metals stick with those. Okay, as we look at this, we're going to make one more big comment here, and we're going to try to make sense of some more of the table. Before moving on, anything about this, I can't tell. Feels okay? Feels awful? Did I lose anybody? So, no, that's okay. I'd like the answer maybe. I would like a more specific answer. I want you guys spend the next 60 seconds, come up with something about what I've covered here that you don't quite get. I'm cool with it. Everybody should probably have something, or that you want to know more about. Something you don't understand or that you want to know more about. 60 seconds, something regarding metals. I heard 2 fantastic questions just now. One of them is much easier to address. The first one is, in the example that I did with sodium, when I lost an electron, where does it go? Because it can't just magically disappear, right? We'll see that part and answer that question here in just a minute, but it's a natural and it's like good question. The second question was, why does metal have different valence electrons? Which that's a much harder question, Sonny. And whether it was Sonny or anybody in that group. Jonah, I'm super thirsty. Will you go get a drink for me? Okay, as we look at this stuff. Yeah, go get me a drink. Water fountain. Cool. All right, so as we're looking at these things, we are going to clear up Lily's question. Sonny, we're going to have to hold off on yours. Okay, metals bond with non-metals. Now, the explanation as to why this would be the case is we see that, hey, metals lose typically 1 to 3 electrons. Okay, because they only have 1 to 3 valence electrons, they typically lose those in the process of what we're about to see. Okay, on the other side, that's a metal. It's lost some electrons. Who picks them up then? So it probably won't be group 18 because they're all completely stable. They don't want any more electrons. 15, 16, 17 is pretty common to look at. And if you look at groups 15, 16, and 17 on your periodic table, metals, non-metals, metalloids. Non-metals. And if it's 15, 16, or 17, then they happen to just need the exact amount to be stable. Non-metals gain them. Okay. This idea we've already hit a little tiny bit just by seeing it. But we are going to go ahead and sneak in one more definition here. And we're getting close to a spot where we'll have to think about pausing or not. I guess we got 15 minutes. Okay. Who in here has heard the word ion? Ion. Okay, Klein's going to fire away a number here, and I'm going to say, hey, I don't care whether you're right or wrong, but I want to know number 17. Have you heard the word ion? Well, darn. Will you try again? That must be Liam. 13. Bless you.
Oh, that's Vinci. It's gone. Oh, wait. Oh. That's Vinci.
You get mine. It is. Keith, have you ever heard the word ion? Okay, so that's all right. Hit it again.
5.
Sonny, have you heard the word ion? Can you tell me anything about it? Where have you heard it? Which context?
It's not about like your brain, right?
It could be about your brain.
That's what I was.
Interesting. So 100%. Sonny's right. You have sodium ion channels in your brain. It's how one nerve sends signals to the next. It's through fancier process that we're going to carry in here. But if you know a little bit about neurology, the study of brain and how those signals are sent, ion will show up. Anybody seen it in a different context, not the brain?
Not an important context.
So if you're going to see it in regular life, science fiction type stuff is where you would probably see it. And I don't know if anybody in here is really into sci-fi. I'm not crazy into sci-fi stuff. Okay, if we don't have a definition for it yet, that's okay. We're going to say an ion. Super easy to define. This, by definition, an ion is simply an atom with a charge. Now, I could include more language here, but I just want to specify. If it's neutral, does it have a charge? If it has no positive or negative, the charge is just 0, right? I would say there's no charge on it. Okay, if I have an extra electron, one more than I should, I would have a -1 charge. If I have one fewer electron, like I remove a -1, I would now have a positive charge. Okay, so ions are atoms with a charge. And in here, we sneak into two different situations. We have follow-up definition, an ion. Two types of ions. We have anions, which this is a silly way that I remember this. A negative ion. So an anion is just simply an atom with a negative charge. Has a negative. We're going to see another one here in a second. An is like anti. I like to think of it as a negative ion. Okay. In contrast with anions, guarantee nobody has seen this one. Okay, I can't guarantee it. But cation.
I thought it was going to be
So we have anions, and right now we're going to talk about cations. If an anion is a negative, what do you think a cation is? Has a positive charge. You would need a U to be caution. I am going to sneak on the word charge on the end here. Okay, so in general, your atoms on the periodic table are neutral. Same protons and electrons, but there's some that are really willing to give up their electrons and become cations, those are positive, or there's some that are really willing to gain extra electrons to get that stability, and we call them anions. Okay, as we look at these, it turns out that when we start letting things interact with one another, we get a ton of expected results that we're going to wind up seeing over and over. So, couple little things here. We're going to look at atoms, and then we're going to pick the group. So we'll say atom and group, or atoms group rather. We're going to make a little table here. And then I want to know the common charge of elements in that group. Because remember, as we look at the periodic table, everything in the same column is going to behave similarly because it's the outer or valence electrons that wind up dictating that. So we're going to pick a few here. And I think we only have like 4 or 5, but I'm going to help you out with the first one, and I want to see if you guys can finish the others. Pick something from the main group. So don't pick anything from the middle yet. From the middle, I'm sorry. The main. So beryllium, that's group 2, right? Okay, so I heard beryllium and hydrogen. I'm going to use group 2. That means we could be talking about beryllium, magnesium, calcium, strontium, barium, or radium? Or radon?
Radium.
Radium, okay. Okay, in group 2, can you tell me how many valence electrons it has? 2, because it's group 2. That's the same, right? Okay, if you were an atom that has 2 valence electrons and you want to be stable, do you ditch 2 or do you go get 6?
Ditch 2.
And if you ditched 2, and that's the easiest thing for you to be stable, you were neutral and you removed 2 negative charges. What's your new charge?
Wait, I was neutral in the...
You were neutral and now you got rid of 2 negatives. You got rid of your 2 electrons. Positive 2. You removed a negative, you now have a positive charge. Minus a negative turns into a plus in math. If somebody's looking at that, and I see at least one look out there, you do not have to draw this, but check it out. If this is 2 protons and 2 electrons, what's the net charge right now?
0.
Because plus 1 is 2, and then minus 1 is 0, right? Okay, if I happen to be stable, or if something random happened, we'll just talk about it. If I get rid of 1, now what's the charge?
Oh wait, is the red proton...
We still have 2 protons and 1 electron.
Never mind, it's just 1.
We removed a negative and it became a positive. This is the explanation for why math works that way rather than just saying it does. We can look at it here. So you guys told me that if we remove 2 electrons, I now have a charge of plus 2. That is what should be expected. Most of the things in group 2, if we were to talk about what's the anticipated charge or how's it going to stick with other stuff, you know that it has a pretty common charge of plus 2. Sorry. Okay, I'm going to give you guys a few more groups. I want you to use the same logic. I'm going to give us, I don't know, maybe 2 minutes. We did group 2. I want you to do group 1. 13, 16, and 17. I want you to tell me for anything in there, if it were to ditch some electrons, for whatever reason, doesn't matter why yet, what would the expected charge be for something in that group? Cool. Talk it out, logic it out. I'm going to be crutching around a little bit so I can answer and help guide if needed. But we'll give it about 90 seconds is my plan. Cool. But hitting it. Let's see. Klein says that number what? Who? Number Max. Can you tell me if you pick something from group 1 and let it get stabilized with the electrons, what would the charge be expected to be? With confidence, I hear plus 1. Can somebody second it?
Yes, plus 1.
Okay. Do you understand why? So check it out. I'm going to steal this for a second. Okay. I'm not going to draw the table this time. Or the element, whoa, I lost it all. All right, that's all right. Whoa, we could do a pre-calc problem. Okay. I mean, I'm sure we'll do it eventually. All right, so check it out. Let's pick something in group 1. I'm going to pick potassium arbitrarily. How many valence electrons does potassium have?
1.
So to be stable, it can either get rid of 1 or it can gain 7. Which is easier? Subtracting 1. So check it out. Right now I have 19 valence electrons, or electrons total, because I assume it's neutral. 19 protons, 19 electrons. If I got rid of 1 electron, I now have 19 protons and 18 electrons. If I were to just get rid of 1 and kick back 1, it would take me here to 18, right? How many valence electrons would that one have? How about just the valence electrons? 8. And would it be stable?
Yes.
It's willing to get rid of its 1 electron to be stable. And it's really common that it does that. Which, as we keep kicking with this, we'll get a little bit more practice. I'm going to steal this for one more second. What about this one? How many does it need to get rid of to be stable? So I count -1, and then if I go -1 more, I have to go down to the previous period first. So we're in period 3, and look at that, I'm stable, and I have a charge of +2 because I've lost 2 negatives. Okay, let's look at another one here. Klein, hit it. Give me the next person. Klein, you're killing me. 15, Ronaldo. If I am in group 13, here I am, group 13. I have 2 options. I can either get rid of 3 or I can gain how many?
5.
I can either get rid of 3 or gain 5. What's easier?
3.
3. So if I got rid of 3, that would put me at, instead of, I don't know which one I was looking at. I'm going to look at this one. If I got rid of 3, I'd be at what number? 10. And if I find element 10 that normally has 10 electrons, does it have 8 valence electrons?
Yeah.
And it's stable. Which means we had to lose 3 electrons, right? If I lost 3 negatives, what happened to my overall charge? So careful. We were neutral, and I removed 3 negatives. So 0 minus subtracting, -3.
Negative. Oh, wait. Minus plus 3.
+3. Okay. On 16. Yep, and it's strange. Okay. We made eye contact, Raylene. We're going to go with this last one, and I realize time's about up. Raylene, group 16 has how many valence electrons? Okay, to be stable, it needs how many? Do I add 2 to 6 or do I subtract 6? What's easier? So if you added 2 negatives, we get a charge of -2. Okay. I will see you cool cats tomorrow.